Okay,
Yeah.
perfect.
Hi, everybody. Parishmita here. Hi, Ravi. There is a little formality before your presentation.
Mhm.
So, on behalf of I team, would like to introduce you to the audience. So, yeah. So, can we start?
Sure. So, hello everyone. Good evening. My name
Sure.
is Ravi.
Yeah.
I'm a
No. I'm sorry. I'm going to introduce you on behalf of all. Yeah, good. So, good evening to one and all present today virtually in this 10th webinar of the Assam Artificial Intelligence Initiative on a topic manipulating emotions, generative modeling for expressive speech synthesis. I welcome you all on behalf of Team I to this event. I is an initiative to promote AI in the Assam Northeastern region and build an academic network for students, researchers, AI enthusiasts to exchange knowledge and share ideas. And today we are delighted to inform you that we have Ravi Shankar with us, who is currently pursuing his PhD in the Department of ECE at Johns Hopkins University, USA. At that university, he is primarily working on emotion conversion in a speech in the context of expressive speech synthesis. His work lies in the intersection of speech signal processing, statistical modeling, and deep learning. Ravi did his undergraduate from Electronics and Electrical Engineering Department of IIT Guwahati, where he had worked on keyboard porting for low resource languages, which was supervised by Professor SRM Prasanna. And he has received the Mines Fellowship Award twice for working on the frontiers of machine learning and data science. He has also received the Dad Wise Fellowship Award in the past for doing a research internship in Germany during his undergraduate studies. And today's in his talk, Rabi will discuss mostly on how generative modeling can be used for manipulating speech emotions. And here I welcome you, Ravi, and the platform is all yours. Thank
Thank
you.
you, Parismita. Such a lovely introduction. So, yeah, good evening, everyone. My name is Ravi. I'm a fifth-year PhD student in the EC department at Johns Hopkins. Today, I'm going to talk about my work on emotion conversion in speech, which is a precursor to expressive speech synthesis. This work has been done in collaboration with CY, Nicola, and Archana Venkatraman. CY and Nicola, they are with the Department of Applied Math and Statistics at Johns Hopkins. And Archana is my faculty advisor. She is also the head of the Neural System Analysis Lab at Johns Hopkins. Okay, so let's start. So why are we doing emotion conversion in speech? Well, there are multiple applications for a emotion conversion module, and one of which is that we can use it as a secondary framework for generating expressive speech using devices such as Amazon Echo or Google Assistant. As such, the speech produced by Amazon Alexa or Google Assistant, they sound very flat or monotone, so we can make them sound more expressive. Second, it can be used to understand or evaluate the quality of human-machine dialogue systems. It has been shown that the prosodic variations can actually help us understand how natural a conversation is between a machine and a human. Third, they can also be used to design therapy for certain cognitive disorders like autism. Autism as such is characterized by reduced emotional perception in speech. Therefore, by using an emotion conversion module, we can design therapy to bring the emotion perception of autistic patients to a healthy individual level. And apart from these, there are many other applications where an emotion conversion module can be used, or in the context of expressive speech synthesis. For example, it can be used for generating audiobooks, which is often a very cumbersome and time-consuming process. So let's look at some of the challenges involved in doing emotion conversion. The first challenge that we have to deal with is the fact that emotions are inherently ambiguous and they are extremely subjective, meaning that our perception depends a lot on our prior understanding or knowledge of the speaker itself. Second, most of the features that we extract from speech, they can be broadly grouped into two classes or two categories. The first one is the prosodic features and the second is the acoustic features. These two feature representations are not orthogonal to each other, meaning you cannot manipulate one without inadvertently affecting the other. So it's really difficult to make sure that when you're changing the prosodic side of the speech signal, the acoustics does not change. And third, there is a significant overlap between the feature representation in the high dimensional manifold that makes learning a mapping function from one emotion to another extremely challenging. So the rest of this talk is organized as follows. First, I'm going to talk about the feature extraction pipeline and some of the prior works that have been done in emotion conversion domain in the background section. Then I'll talk about our own modeling approach, followed by the experimental results. And then I'll finally conclude the presentation and talk about some of the future work that we plan to do. So let's dive right into the background section. So for the feature extraction, or the analysis pipeline of our model looks like this. Given a speech signal or an input speech, we use the word vocoder to decompose it into three components, namely spectral envelope, F0 or fundamental frequency contour, and aperiodicity. So this decomposition is based on the source and filter theory of the speech signals. The spectral envelope belongs to the group of acoustic features, and that is mainly responsible for the sound which is being produced. You can also think of it as the filter response of the vocal tract system. The F0 contour is the variation of pitch over an utterance, so it controls the intonation. And F0 contour and aperiodicity together forms the excitation part of the signal. So F0 contour and aperiodicity, you can think of it as the input signal to the vocal tract system, which leads to the generation of speech signal. From spectral envelope, we can derive or we can extract what is called as the energy contour, that is the variation of loudness over an utterance. And F0 contour and energy contour, they belong to the group of prosodic features. So these features are mainly important from the emotion perception standpoint, because as I mentioned, F0 contour controls the intonation, meaning how high or low you are going with your tone. And the energy contour controls the variation of loudness. So here is how a typical emotion conversion pipeline looks like. And in fact, the conversion pipeline is very similar for voice conversion too. So suppose we are given an utterance in some emotion category A, then we first decompose it into the spectral components and the pitch contour. Then we have a separate model for spectrum conversion that converts the spectrum from emotion category A to emotion category B. We have a separate model for pitch that converts it from the source to the target emotion. And aperiodicity as such does not play any role in the perception of emotion. So we directly copy it from the source. Then once we have the components in the target emotion domain, we can reconstruct the speech using the word vocoder. So for the purpose of this talk, I'm mainly going to focus on the pitch model because of the mathematical simplicity, and also because the spectrum model is completely analogous to the pitch model. So we are not losing any information there. Okay, so let's look at some of the prior works that have been done in the domain of emotion conversion. And in fact, most of these works can be broadly grouped into three categories. The first one is the statistical conversion, which involves learning some kind of a joint density framework for the source emotion and the target emotion features. The second one is a more direct approach, which uses a neural network like CNN LSTM model to learn the conditional density of the target emotion features directly. And the third is a more recent trend, which belongs to the group of unsupervised learning, and they typically use a GAN or a VAE model to learn the conditional density of the target emotion features. Okay, so let's look at the statistical conversion models in more detail. Since this is a supervised learning framework, we require parallel utterances in multiple emotion categories. And given these parallel utterances, we can extract the relevant features. Then once we have the relevant features, then we jointly model them using a Gaussian mixture model or a kernel density model. Then during inference, we condition on the source emotion features to get the expected value of the target emotion features to reconstruct the speech in the target emotion. The second one is, again, it's a supervised framework. I'm calling it neural emotion morphing. In this framework, we again require parallel data. And most of the frameworks are either CNN or LSTM based, although recently highway neural networks have also been used to learn the target feature conditional distribution directly. So the third one is a more interesting framework. It's a supervised conversion technique, meaning we no longer require parallel data or parallel utterances in the source and the target emotion category. And the underlying idea is very similar to the neural emotion morphing. We are still learning the conditional density of the target emotion features, but now it's in an unsupervised framework. So I'll talk more about this framework in the next few slides, because in fact this forms the backbone of our proposed model as well. Okay, so here's a primer on generative adversarial networks. And the reason why I'm talking about GANs is because our model is basically a derivative of the GAN model. So in GANs, we typically have a generator whose task is to take in an isotropic Gaussian noise as its input and learn, or rather sample, from the target data distribution. The error feedback in generator is obtained by using a classifier, also called the discriminator, whose job is to basically identify a sample as either belonging to the data distribution or a sample which does not. So the generator and the discriminator, they are tied together by the min-max objective function, which is shown here in the middle. The task of the generator is to minimize this loss function with respect to its parameters, denoted here by theta, whereas the task of the discriminator is to maximize this loss with respect to its own parameters, represented here by parameter phi. And just for clarity, we are using P of X to denote the distribution of the data that we have. And P theta of X is the distribution that the generator manages to learn. Okay, so the next framework that I want to discuss is a Cyclegain model. A Cyclegain model is an extension of GAN, and they're typically used for domain transformation tasks. So for example, if you have two domains, let's say a domain of natural images and a domain of paintings, and if you want to transform from one domain to another without changing the content of the input data, then Cyclegain is the way to go. So what happens in Cyclegain is that there is a pair of generator and a pair of discriminator. Let's suppose the domains are represented here by domain X and domain Y. Then the generator which transforms from domain X to domain Y is represented here by generator G gamma, also called the forward transformation. And the generator which transforms from domain Y to domain X is denoted here by generator G theta, also called the backward generator. Then the most important element, or the most crucial element of Cyclegain framework is this loss term called the cyclic consistency loss. So what the cyclic consistency loss does is it constrains the generative process of the two generators by dictating, or by sort of making sure that given an input sample, when it goes through a full cyclic transformation, which is denoted here by cascade of the two generators, G theta and G gamma, the sample, or the cascaded sample, should look very similar to itself. So it enforces a kind of consistency between an input sample and the generator, or a cyclic counterpart of it. The discriminator in Cyclegain is the same marginal density discriminator that we have seen in the vanilla GANs. So there is no difference there. Once again, just to remind you, we are representing P of X here now represents our distribution of the source pitch contour, and P of Y represents the distribution of the target emotion pitch contour. P theta of X is the distribution that our generator G theta learns, and P gamma of Y is the distribution that our generator G gamma learns. And by the way, if you have any questions, feel free to stop me anywhere and yeah, just shoot it at me. Okay, so let's look at our modeling approach. So the first thing that we realized after looking at the cyclic consistency loss is that it's a sample-wise loss, meaning that it cannot enforce a strong dependency between the two generators. So our first proposition is that the expected cyclic consistency loss is merely an upper bound on the first order moment matching between a data distribution and cyclic counterpart, meaning that doesn't really do much except for enforcing that the means of the distribution match. So that's a very weak constraint. Like, it's just the first order moment matching between the two distributions. The second proposition we have is that under the ideal conditions and the assumption that the sampling noise is Gaussian or even sub-Gaussian, the expected cycle consistency loss does not go down to zero unless the generators become deterministic. So you have to sacrifice the generative aspect of the model in order for this loss, the cycle consistency loss, to go down to zero. And in fact, the situation gets even worse when there is high dimensional data involved, because if you compute the expected cycle consistency loss under the assumption that the model has been trained well, then you get a dependency on the number of dimensions. So these are problematic. These are the real issues with the cycle consistency loss, which people have not realized. And yeah, we try to address these problems in our variational framework that I'll discuss next. So apart from these two propositions, there is another one. It's rather a hypothesis that we have come up with. We haven't been able to check it, but it's the fact that if you look at the Cyclegain model, here. So the generators in the Cyclegain model, since they're tied together by this cycle consistency loss, they have an extra information in terms of the min-max game that the generators and the discriminators are playing. So the generators are aware of the fact that there exists a complementary generator from which I'm going to get an error feedback. Whereas the discriminators, they have no clue whatsoever that there is a complementary generator that exists in the framework. So the nature of the min-max game should be such that it's fair for both players that are engaged in the game. Whereas in this case, the generators have an extra information, whereas the discriminators don't ever get to see the fact that there is a complementary generator. So yeah, we try to address all of these problems or issues with the cycle consistency loss. So our approach, since it is based on Cyclegain, we are obviously going to have a generator and a discriminator. Our generator is going to take in the pitch contour and the spectrum information from the source emotion, and it's going to give us the pitch contour in the target emotion. Our discriminator is going to do something different, fundamentally different from what vanilla Cyclegain does. So let's look at our modeling. Okay, so immediately upon looking at the data distribution and the distributions which are learned by the generators G theta and G gamma, we can realize one thing, that we can make the dependency between the two generators stronger. So instead of using a cycle consistency loss, or in addition to using a cycle consistency loss, we use a KL divergence based objective for the data distribution P of X and its cyclic counterpart denoted here by P theta of X. And similarly for generator G theta, we have a KL divergence based penalty between P of Y, which is the input distribution of the generator G theta, and P gamma of Y, which is the learned target distribution of generator G gamma. So you can stare at this loss function. If you look at LG of gamma, the loss for G gamma depends on what the generator G theta is going to learn, and the loss for generator G theta depends on what the generator G gamma is going to learn. So there is an implicit tying of the two generators, and this tying is more stronger, or we'll see in the experiment section. This tying is in fact stronger than the cycle consistency loss, and it ensures a fairer dynamics of the min-max objective that the generators and discriminators are playing. Okay, once again, to remind you, P of X and P of Y are the data distributions of the pitch contours in this context. P theta and P gamma are the learnable target distributions. Okay, so using the law of total probability, we can write the parameterized version of the data distribution P of X as P theta of X given Y and P of Y, where we are marginalizing over the random variable Y. Then after some algebraic manipulation, we and using the Jensen's inequality, we get this upper bound on the KL divergence penalty. So the reason why we are doing this is because the KL divergence involves integral over the distribution P of x, and then the integral is in fact intractable. So we cannot directly minimize the KL divergence penalty. So we resort to the to a variational bound on the KL divergence penalty. So the final objective term is shown here in the red box. I want you guys to focus on the numerator and the denominator. So if you look at the objective in the red box, it's basically a log ratio of distributions of x and y. In the numerator, we have the joint density of x and y, but it's been factorized from the perspective of generator g theta. And then in the denominator, we have the same joint density, but it's been factorized from the perspective of generator g gamma. So that leads us to a different kind of discriminator formulation. And in fact, our discriminator, instead of classifying between the marginal densities of x and the distribution that the generator g gamma learns or g theta learns, we are instead classifying between the joint densities here. So our discriminator is going to take in a pair of samples instead of just one sample, and it's going to classify it as either belonging to one type of factorization versus belonging to the second type of factorization. So yeah, our discriminator is going to take in a pair of samples, and we implement this discriminator by using a fully convolutional neural network, which has instance normalization and gated linear unit, just to make sure that the backpropagation and the training is faster. Okay, the second contribution that we have made in this particular work is that we are modeling the target emotion pitch contour as a smooth diffeomorphic warping of the source pitch contour. So if you look at this figure on the screen, we have the pitch contour in the source emotion denoted by the red curve, and we have the pitch contour in the target emotion denoted by the blue curve. There is a significant gap between the two, and as such, it's really extremely difficult to bridge this gap if you're using if you're trying to predict the target emotion pitch contour directly using a generator. So we have to come up with something more novel, because just bridging this gap or estimating this range or the difference between the two pitch contours is extremely difficult. So what we do instead is that we model the target emotion pitch contour as a smooth diffeomorphic warping of the source pitch contour. A typical diffeomorphic process takes in the source pitch contour and warps it iteratively over multiple time steps to match it exactly with the target pitch contour. So if you look at the figure on the right, that's exactly what the process is doing. It's taking in the source pitch contour and modifying it iteratively over multiple time steps to make it look like the target pitch contour. Now, the nice thing about this diffeomorphic warping is that it is completely parameterizable, and in fact, you can parameterize it by using this using a latent variable called the momenta, which has the exact same dimensionality as the pitch contour itself. So if you look at the figure on the right, the black arrows on top of the red curve, they represent the momenta variable at each point of the curve. So since they are pointing upwards, meaning that the red curve has to move upwards. And yeah, if you look at towards the tail or towards the end of the red curve, the magnitude of the momenta variables are really small, meaning that they don't really have to move much over as we iterate over the time steps or as we deform the curve. So yeah, here is the key takeaway from this pitch contour modeling. Instead of directly predicting the target emotion pitch contour, we have an intermediate variable, the momenta variable, which has the same dimensionality as the pitch contour itself. So we are going to predict this momenta variable or the intermediate, and the knowledge of this intermediate variable along with the source pitch contour completely specifies the target pitch contour. So that's it. Okay. Now that we have introduced a latent variable as an intermediate step, our generative block is going to be composed of two components. The first one is a stochastic block, which is going to sample the momenta variable. The second one is an LDDMM block, which is going to take in the pitch contour and the momenta estimates, and then do the diffeomorphic warping process. So the stochastic block is again implemented by a fully convolutional neural network with residual connections so that backpropagation is easier. The LDDMM block, because of its iterative nature, can be represented by an RNN block. So the hidden state of the RNN is the momenta itself, and the output at each time step is the modified version or the warped version of the input pitch contour. So you can think of running this RNN model for t number of time steps, and the output at the end of t time steps is going to be the target pitch contour. Okay, so let's look at our training approach. So first we sample the pitch contour in source and target emotion, the pitch contour and the spectrum in the source and the target emotion domain. Then using this information, we input these pitch contours and the spectrum information to our stochastic block, which samples the momenta. Then once we have the momentas, we warp the input pitch contours using the momenta to get the target emotion pitch contours. And then once we have the pitch contours, we feed it to the discriminator, and then the discriminator gives us the error feedback, and then we backpropagate through the whole framework. And in fact, we also backpropagate through the LDDMM module to train the stochastic block. So what I have shown you so far is a simplified version of our complete model. And the figure you are seeing on the screen right now is the complete graphical representation of our model. So given the pitch contour and the spectrum in the source emotion, we estimate the pitch momenta or the latent variable that I mentioned. Once we have this latent variable, then we estimate the target pitch contour. And we repeat the process for the energy contour. And once we have the energy contour from the modified energy, we get the modified spectrum. So we are not directly modifying the spectrum, rather we are indirectly modifying the spectrum by modifying the energy component. And our KL divergence penalty is actually, it's a penalty on the joint distribution of the spectrum and the pitch contour. And we use some of the conditional independencies that we can read from the graph itself. For example, SB is conditionally independent, or the spectrum in domain B is conditionally independent of the pitch contour in domain A, given the spectrum in domain A and pitch contour in domain B. And we have a similar conditional independence that relates the pitch contour in domain A, pitch contour in domain B, and the spectrum in domain A. And using these conditional independence assumption and the variational lower bound, we are able to split the generator loss into two components, one for the spectrum and the other one for the pitch contour. And this is the complete model that we are using, or we are working with at the moment. So we have the pitch contour and the spectrum. There is this F0 stochastic block, which samples the momenta for pitch contour. Then we feed the sampled momenta and the pitch contour to the generative block, or the LDDMM block, to generate the pitch contour in the target emotion. Then once we have the pitch contour in the target emotion, we feed it along with the spectrum in the source emotion to generate the momenta for the energy contour. And then we modify the energy and indirectly modify the spectrum to get the spectrum in the target domain. And as I mentioned, we have two different discriminators, one for the pitch and another one for the spectrum. Okay, so as I mentioned before that in a vanilla Cyclegain, the cyclic consistency loss is kind of screwing us up. And the reason is that it allows the generator to use the fact that there is a complementary generator for them to work with, whereas the discriminators never get to see that. So the dynamics of the min-max game is unbalanced. Whereas in our case, the discriminator itself is going to use the fact that there are two generators in the model. So since the generators are able to use the complementary generator for their error feedback, the discriminator should also have this information that there exists a complementary generator in the Cyclegain framework. Therefore, what you're seeing in the plot here is the discriminator loss and the generator loss, which are sort of balancing at the optimal value of the game, which happens to be 0.5 in this case, because they both can go from 0 to 1. And what we are trying to show here is that this balancing between the two losses is very rarely seen in GANs or even in Cyclegans. So the fact that we were able to get that means that our model is actually well calibrated. And the figure on the right here shows an example of the pitch contour sampled from our model. So the figure on the left, the red curve or the orange curve is actually what the model generates in the target emotion. And you can see that since this was from the validation set where we have some parallel utterances available to us, you can see that there seems to be some kind of one-to-one correspondence between the pitch contour representations in the source and the target emotion domain, and the variational Cyclegain model that we have proposed is somehow able to uncover that relationship between the two. So it was really interesting to see that conditioning on the spectrum, there might be a one-to-one relationship between the pitch contours, which definitely is not the case if we don't condition on the acoustic features. Okay, so let's look at the experimental results now. Actually, before I talk about the experimental results, let me just give you some idea about the dataset that we are working with. So we are using this dataset called VSUS dataset, which we collected here at Hopkins in my first year. The dataset contains emotional utterances from 4 different emotion categories, namely neutral to angry, neutral, angry, sad, and happy. Then each emotion class has 250 phrases spoken by 10 different actors, 5 male and 5 female. Then each utterance in the VSUS dataset comes with 10 manual annotations that we obtained from Amazon Mechanical Turk. So we made people on Mechanical Turk listen to each utterance in the VSUS dataset and rate the saliency of the portrayed emotion in those utterances. And in fact, for our experiments, we are sub-selecting the utterances so that we only pick those which have high saliency rating, or which were or the utterances in which the target or the intended emotion was portrayed and was rated correctly by at least 50% of the Amazon Mechanical Turk listeners. Okay, so we'll talk about our evaluation metric now, which is mainly subjective. But before that, since our goal is to take in a synthesized speech or a neutral speech and make it sound more emotional, we are doing experiments with 3 different pairs of emotion. The first one is neutral to angry, the second is neutral to happy, and third is neutral to sad. So our first subjective evaluation is the crowdsource-based emotion recognition task. So what we do in this task is we let the listeners or let the raters on Amazon Mechanical Turk listen to our neutral speech and our converted speech, and then we ask them to identify the emotion in those 2 utterances. So the reason we give them neutral speech is because we want to eliminate some kind of speaker bias, or give them some hint about the speaker's neutral state. Because as I mentioned, our perception depends a lot on our prior understanding of the speaker itself. The second evaluation metric is again a subjective evaluation task, and this is the crowdsource-based reconstruction quality assessment. So we are trying to see how good our model is able to reconstruct this, or is able to reconstruct the, or how good the quality of the reconstructed speech is. Yeah, and we carry out these experiments for human speech from the VSUS dataset. We have some synthesized speech using WaveNet model, and then our baselines are a GMM-based model, a bi-LSTM model, and a vanilla Cyclegain, which have been proposed in the past. Okay, so let's look at some of the baselines that we compare our result against. The first one is a GMM-based model, which takes in the pitch contour of the source emotion and the spectrum of the source emotion, and the pitch contour and spectrum of the target emotion, does a joint modeling using a Gaussian mixture model. Then during inference, it estimates the pitch and the spectrum of the target emotion by conditioning on the source. The second baseline is a bi-LSTM-based model, which takes in the pitch contour and the energy contour and does a discrete wavelet parameterization of these two features. So the discrete wavelet parameterization allows them to learn a segmental and the suprasegmental properties of the pitch and the energy contour. The third one is a Cyclegain-based model, which again does the discrete wavelet parameterization of the pitch contour. And they modify the spectrum using the exact same model, but it's trained in a disjoint manner. So they have two separate models, one for pitch, one for spectrum, and they do it for each pair of the emotion. Okay, so here is the result of our model on the VSIS dataset, meaning human speech. So the first thing to notice here is that the Cyclegain model and the variational Cyclegain model, they are both able to perform really well in comparison to the bi-LSTM and GMM model. And that shows that these unsupervised learning frameworks are fairly expressive, meaning that you can actually achieve a lot by either using the type of neural networks they use or by using the min-max objective that these frameworks typically use. So the second thing to note here is that the GMM model seems to be doing well, but this is so we found that it was almost impossible to generate intelligible speech using GMM model when we trained it in a multi-speaker framework. So we had to train the model for each speaker individually. So these results are not really indicative of the performance of GMM model, because we had to train it for each speaker individually, whereas the rest of the models were trained in a multi-speaker setting. And as you can see, our proposed model, which is variational Cyclegain, does a fairly good job of converting emotions, of changing neutral emotion to angry and neutral to sad. However, it does slightly worse on the neutral to happy emotion. But we figured the main reason was that we had less than half the amount of data for training neutral to happy conversion as compared to neutral to angry and neutral to sad. Then the second subjective evaluation, which is the assessment of the reconstruction quality. As you can see that our model does extremely good job of maintaining the quality of the synthesized speech or the quality of the converted speech. So we also did some experiments with the synthesized speech, which is an out-of-sample speaker realized by the WaveNet model. As you can see, in this case, our model actually shines, it stands out in comparison to the bi-LSTM and Cyclegain model. We didn't use GMM model here because as such, it's not able to generate intelligible speech when it's not trained on that particular speaker. So it has 0 out of sample generalization. Whereas our model, since it does not depend on the cohort-based statistics normalization, it's able to generalize to an unseen speaker. Also, the fact that we are modeling the target pitch contour as a diffeomorphic warping, it's able to capture the range or the variation in the pitch of a speaker in a better manner than the other baseline methods we have seen so far. Once again, the quality of the speech is reasonably well. The bi-LSTM model seems to have really high quality, but again, it's not doing anything. It's learning an identity mapping, so that's expected. Okay, I have some conversion demo which I wanted to play for this talk, although I'm not sure how can I do it. So I'm just going to remove my earphone and play these audio files at high volume on my laptop. Okay, so the first one is neutral to angry conversion. on the Visas dataset samples. So let me play the neutral speech.
4th of July.
Is it audible?
Yes, it is audible, Ravi.
Perfect. Thank you.
Good.
So yeah, let me play the neutral speech once again.
4th of July.
And this is the converted angry speech.
4th of July.
As you can see, the loudness goes up in the beginning of this of the utterance, and then goes down a little, and then it again goes up towards the end. So our model is able to capture this variation in the loudness profile. Okay. The second is neutral to happy conversion. So let me play the neutral speech first.
9.
Let me play it once again.
9.
And the converted sample is
9. 9.
Yeah, so the immediate thing you can realize from these two samples is that the neutral speech sample sounds very flat. There is no intonation as such. It's flat and monotonic. Whereas in the happy case, it appears that the pitch is actually going up towards the end of the utterance. And the third sample we have is for neutral to sad conversion. So let's play the neutral one.
They smell bread.
And the converted sample.
They smell bread.
So our model is able to capture that quivering effect that we typically see when a person is in sad emotion state. So these are the examples on the Visas dataset. We have some examples on the wavelet synthesized speech. So let me play neutral to angry on the wavelet speech.
The deer cross the stream. The deer cross the stream.
Yeah, the quality of speech does go down a little, but at least it's able to inject some kind of a prosodic variation from the neutral speech. So let me play the angry converted sample once again.
The deer cross the stream.
Yeah, there is an emphasis on crosses part. So it appears that the pitch and the energy both actually go high towards the middle of the utterance, and then it comes back down. And we have neutral to happy conversion.
Carol designed map.
And the converted sample sounds like this.
Carol designed map.
Yeah, the person appears to be in a more excited state, although it's debatable whether it's happy or something else, but there is definitely an increase in the enthusiasm level. Or yeah, the speaker appears to be in an excited state, at least. And the last one is neutral to sad conversion. So this is the neutral speech.
Their chocolate is brown.
And the converted sad sample.
Their chocolate is brown.
Yeah, so the sad sample in the wavelet speech does not have the exact same quivering effect as the sad sample in the human speech, which means that our model is actually learning a variation, or rather it's not learning an average representation of the emotion itself. So that's a very interesting thing that we have noticed in this variational framework, that it doesn't learn just an average representation of the emotion, which is often the case with a lot of these generative models like VAEs or GANs. Okay, so in conclusion, I can say that we have proposed a variational Cyclegain model for emotion morphing. Our model consists of a hybrid generator and a pair density discriminator, which is fundamentally different from vanilla GANs or vanilla Cyclegans. Then we are also able to show that our model generalizes well on unseen speakers, which was realized using a wavenet model. And this is mainly due to the fact that we are modeling the target emotion, pitch contour, or prosodic features by using a diffeomorphic model. So currently I am working on a duration model. So far we have been successful in modifying the energy and pitch. Duration is another component that has a significant impact on the perception of emotion. So we have already, one of our work is currently under review in ICLR, which is a Bayesian framework for adaptive speech duration modification. So this is a more general purpose model that we have proposed for just manipulating the duration and can be used for either voice conversion, accent conversion, or emotion conversion. So yeah, that concludes my talk. Thank you very much for listening. Yeah, now I can take questions if you have any. Hello.
Hello.
Yeah.
Yes, Ravi. Can we take a few questions?
From the email that you sent me.
Yeah, that
Sure.
we can take.
Yeah. Yeah. So let me go over these questions one by one. So Bhaiya asked me to go deep into mathematics, but it was already too late. I could have shown some of the proofs of the propositions that I mentioned in the slides, and maybe gone through the derivation part. But it's more of an algebraic exercise than, yeah. I don't think it would have any meaningful contribution for the purpose of a talk. Okay, so let's look at the first question. What keep you interested in your BTech in the area of speech processing? That's an interesting question, because the reason why I was interested in working in the domain of speech processing is because I really liked signal processing, and the fact that speech processing actually allowed me to work with signals, and it allowed me to work with machine learning models. I was really excited about working on machine learning models and learning more about them. So yeah, speech processing is it's combining the best of both worlds: signal processing and machine learning. What more could I have asked for? I don't know. So what motivated you for a PhD? Well, my motivation mainly comes from the fact that I have spent some time in the industry as well. And I realized that industry, while it's obviously monetarily more rewarding than a PhD for sure, but I wanted to learn more math, understand more statistics, more understand the underlying ideas behind some of the machine learning models like SVMs, GMMs, kernel density estimates, things like that. So I thought, okay, PhD seems to be the right career path for me, because I was curious enough to devote some time to learning these frameworks. Is doing PhD directly after bachelor's a bad move? No, it's not. In fact, a lot of PhD students here at Hopkins, they come directly after their bachelor's. So it's not a bad move. Still, people use Kaldi-based HMDNN models in ASR speech processing or end-to-end. So I know some of the people here in CLSP, Center for Language and Speech Processing, they're still using Kaldi-based HMDNN models, but the objective is slightly different. They are trying to come up with models that can work or perform well in noisy scenarios, whereas end-to-end deep learning models have been on the rise, and I think they are probably way to go in the future, especially the RNN transducer model and the conformer model. I think they have shown some really good performance in the last few years. Plans after PhD. Well, right now I'm looking for internship, so maybe after that I'll decide whether I want to stay in academia or go for an industry position. How much does contributing to open source projects matter? So since we are mainly working we are mainly coming up with algorithms and developing softwares, and we are kind of in the computer science domain, I think it makes sense for us to publish our work or put the code on GitHub so that other people can actually reproduce our work. That brings a certain transparency to the research that we are doing. And yeah, it almost always feels good whenever someone gives you a star rating on your GitHub code page. So yeah, I think you should definitely contribute to open source projects if you can, unless you're working for an industry and you cannot publish or cannot put your code on GitHub for other people to use. How to stay motivated and not procrastinate in research area? This is a very difficult question because I think everyone goes through, like there are definitely phases during your PhD when you will feel like you are not good enough or you are down. And sometimes that can be damaging. So I think a good way to stay motivated is to keep pursuing your goals, like have short-term goals instead of having one long-term goal. Have small milestones, and if you keep achieving those small milestones, it could be anything, right? It could be solving this one exercise problem from a course. So just achieving those small milestones sometimes help a lot. They give you a dopamine boost, so it will keep you, well, it won't keep you motivated as much as you expect them to, but at least it won't affect you in any negative way. So yeah, having short-term goals actually help a lot. So honest advice for a student final year of bachelor who wants to follow the same path as you: turn out if things get out of hand. Okay, so in academia, I think the competition is ruthless. I mean, that's true for industry as well, but in industry, I think it's the fact that you don't have as much pressure on you from your supervisor in academia, in industry, but in academia, the competition is ruthless. There's always a chance of getting scooped up. So think of it as you have an idea and you're working tirelessly to make sure your idea works, and then someone shows or someone publishes a paper before you. So all the work that you have put behind showing that your idea actually works is kind of in vain, right? So there is always a chance of getting scooped in academia, and that, I mean, it has its own it can be very damaging. That's what I want to say. But you have to just keep your head down and keep doing things and just keep learning. What is the metric for telling that a specific emotion is present in? So as I mentioned in the evaluation metric of my talk, we are mainly doing it by putting the audio files on the Amazon Mechanical Turk and asking people to listen to those, and then rate the perceived emotion in those audio files. How emotions can be compared in natural and synthesized speech. I am not really sure what exactly this question means, but I'm not really sure what this question means, how emotions can be compared in natural and synthesized speech. So you can always listen to the audio file and you can see how do you perceive, what emotion do you perceive in the natural speech or the synthesized speech. And the comparison is mainly based on you make 10 people listen to your audio file, and then depending on how many people say that, okay, this does sound like angry or this does sound like sad, then you can come up with a number to show that, okay, 5 out of 10 people have said that, okay, this sounds like angry in the natural speech, and in the synthesized speech, maybe it's 6 out of 10 people. So you can say, okay, there is definitely the emotion is getting portrayed strongly in the synthesized speech. What if machine starts thinking about anything?
Ravi, maybe he is asking about like objective way of comparing, maybe like in speech you do, right? Maybe.
Yeah, so objectively, I think you can use an emotion recognition model to do that. Although the problem with speech emotion recognition models is that they are not really good. Like the average accuracy, I think, on EmoCap dataset hovers around 60-65%. So I think having a listening task, making people listen to your audio files, I think that actually that gives you a better indication of the performance of your model than just using an emotion recognition model. If that answers your question.
Yeah, maybe.
Yeah. So yeah, we don't use emotion recognition models, although I think it doesn't cost us anything. It's cheap, but the kind of results that you get from emotion recognition model, I think I think it can give you a false sense of performance of your own model. So I always try to put it on Amazon Mechanical Turk and then see how my audio files are getting rated there. To fear or maybe jealous or maybe after experiencing certain emotions. Well, it's an interesting question, but I don't really know how to answer this because it seems like we're getting into territory of machine intelligence, although none of my work are actually they are related to general AI or machine intelligence. We have a very simple task. Given a neutral speech or a monotone speech, we want to make it sound expressive, and that's it. There is no fundamental understanding of the content of the speech itself that the model is supposed to have. So I hope that answers this question.
Okay. Ravi, I have one question. I put this in chat box.
Oh, can we check or visualize which part of speech model gives more emphasis? Yes, so we have been doing that. So we are actually, so in our most recent work, we are actually modifying the acoustic, not the acoustic part, sorry. So we are never modifying the acoustic part of the signal because we don't want to modify the content itself. We are only modifying the prosodic features. And we have multiple prosodic features. So we have the pitch contour, the energy contour, and we are also adding the duration component. But in our latest work, we are doing an ablation study where we see how only modifying the pitch contour works versus modifying both the pitch contour and the energy contour. So if that answers your question.
Yeah, okay, thank you. So yeah, I think we are at the end of our session. So Ravi, it was a very excellent session and it was quite informative.
Mm-hmm.
So
thank you very much for inviting me.
Any other point to you want to mention?
Not right now.
Yeah, okay, fine.
Yeah, not right now. If you are curious about our Bayesian framework for speech duration modification, I think I have already shared my slides with you, so maybe you can circulate it with the people who have attended the talk.
Yes.
And,
Okay. Thank you, Ruby, for your nice talk, nice presentation. And in future also, I'll invite you for delivering sessions in maybe other topics as well apart from emotion. Okay.
mm-hmm.
Thank you.
Sure. Yeah. No problem. Thank you for inviting me.
Thank you, Ruby. Thank you. Sasan, I think you can stop the live stream. Maybe.